All right. Welcome, everybody, and thanks for attending the second week of our symposium for February. This week's theme is computation and welfare policymaking. And today we are fortunate to have Professor Daniel Björkegren from Brown's Department of Economics for our keynote address. We will then continue today's program having young researcher Jessica Dye presenting her research on fair machine learning under partial compliance. On Friday, we will continue this discussion at 11:30 with 5 other young researchers presenting their work on topics related to computation and welfare policymaking. So let me start today's program by introducing Professor Daniel Björkegren. Professor Daniel Björkegren is an assistant professor of economics at Brown University. In his research, he explores the opportunities generated by new technologies in the developing world. And he's working on methods to manage dominant networks and to make machine learning more humane. He holds a PhD in economics from Harvard University and a bachelor's degree in physics from the University of Washington. Today, Professor Björkegren is going to tell us about his work on manipulation-proof machine learning. So before I leave the stage to Professor Björkegren, I would like to ask the audience to either raise their hands, like by the Zoom option, or type in the chat if they have questions. Then we will pause occasionally in the talk to answer the questions. So if that feels okay, I will leave the stage to Daniel.
Great, thank you so much for having me, and excited to chat with you all today.
Thanks for accepting our invitation.
So this project is called Manipulation-Proof Machine Learning, and this is joint work with Josh Blumenstock at UC Berkeley and Samson Knight, who's a grad student here at Brown. And Samson will actually also be presenting another paper on Friday to this community. So look out for that. So this project starts from a premise that is common in a lot of concerns about fairness, which is that increasingly a lot of decisions are being made by algorithms. Algorithms increasingly decide what content people see online, who gets a job, who gets released from criminal justice, and many more. And these algorithms typically work in 2 steps. So first, the person or the institution that's training the algorithm observes some training data. And so they see some behaviors X and tries to link those to some outcomes. And for a running example in this talk, we're going to think about credit scoring. And so the outcome we're going to look at is whether you've repaid a loan. And the behaviors could be how you use your cell phone for alternative credit scoring, or you may be more familiar with traditional credit scoring. We basically want to figure out, if we just see these behaviors, how can we predict your outcome? And so based on that training data, we are then going to estimate a decision rule that predicts y hat, what is your likelihood to repay a loan, for example, based on that behavior. And then we're going to use that to make decisions for other people. Now, this leads to 2 problems. The first is that once this decision rule is implemented, it can be gamed. And if the stakes are high enough, I may decide that if I know that the number of Facebook friends I have, for example, affects whether I'll get a loan, I may go make a bunch of friends on Facebook. And so really, it's not just that y hat is a function of x's, but these x's are actually going to be a function of our y hat. And the second issue is that these decisions also tend to be made in black boxes. And we'll dig into that in a slide. So on this first concern, across the board, wherever you see these algorithms being used to make consequential decisions, you see people trying to game them. Firms spend billions of dollars trying to game where they appear on Google search engine results, and likewise, lots of investment in gaming Facebook's algorithms and Instagram. Insurers have tried to use new algorithms like this to figure out who is making healthy life choices. And so some insurers give a discount based on a step count. So if your phone says you've stepped or walked enough each day. And so then people found out that people started using this device,
池塘边的榕树上，知了正声声地叫着夏天。
which takes you steps for you. And so some of these examples may seem kind of fun or interesting, but this manipulation can have serious implications. So in the examples we're really looking at later, digital lenders have found that their portfolios, which they thought were reasonable, are swamped with fraud. We've had cases of social networks being overrun with content that's been engineered to be visible. It's possible to trick self-driving cars into crashing by subtly modifying stop signs so that they're no longer recognized as stop signs. So manipulation is a problem across the board. And relatedly, these algorithms are typically kept as black boxes. And that leads to two concerns. First, that individuals may deserve some right to explanation. So if I was denied a loan or denied bail, maybe I deserve some rationale for that. And second, at a societal level, we may want to be able to inspect these decision rules to understand whether they have bias encoded in them. And this type of right to explanation has been encoded in the GDPR in the EU, which guarantees some meaningful information about the logic involved in automated decision-making. And there's a lot of debate about whether we should have those rules in other regions as well, and how strong these should be. But one of the issues is that the more you reveal about how these decisions are made, the easier these decisions are to game. And that can make it impractical to make decisions using these methods. And the current way of training these machine learning models can lead to quite bad outcomes if we just made these rules transparent. So this project asks the question, can we build equilibrium decision rules that are robust to manipulation, even if we make them fully transparent and we tell people exactly how these decisions are made? And it has two parts. So first, we're going to show you a theory, which is a way to solve for optimal decision rules. And we'll have a method here that solves for that, given the cost of manipulating different behaviors. And then we're going to test it in the field. And we did a field experiment in Kenya where we both estimated these costs of manipulating different types of behavior and tested out this Saturday robust algorithm. And foreshadowing it, we found out it does quite well. So this project builds on a lot of related work. The most closely related work in economics is the Lucas critique, which suggests that if you observe some correlation in data, if you then act on that correlation, then that pattern that you observed in the data may no longer be there. So taking actions can modify the world you're trying to analyze. And there's also some work in mechanism design and contract theory. And also in computer science, this problem has been often called strategic classification. And it's also closely related to adversarial machine learning. And the contribution of this talk is to, most of this literature here is theoretical. The contribution of this talk is to use a model or develop a model that we can actually estimate with data and then test it in the real world. And so you'll see a lot of commonalities between these theoretical papers and what we do. Now manipulation is not a new problem, and anyone in the tech industry will be facing this problem if they're making automated decisions. And so you might think of two ways to address this. So the first might be a theory-based approach. And we might sit down and say, we're going to think about all of the features that we might include in our model and think about whether there are some that are too easy to manipulate. And if so, we'll just omit those. And so this is an approach that might be familiar to economists. This has two problems. The first is that nearly all behaviors or all features are manipulable at some cost. And the second is that this may have worked fine if you think about traditional credit scoring, where you might have 15 or 20 indicators you might choose from. But if you look at modern data sets with thousands of indicators, it's just very difficult to know where to begin. And so in practice, what firms typically do, and what we're going to call the industry approach, has two parts. So the first is that they keep their decision rules secret, or security through obscurity. And so then you can train your model. But if the stakes are high enough, then people will typically figure out ways to game that decision rule. And so this industry approach typically retrains these models periodically. And so after people may have figured out part of how to game this initial rule, then we'll see an altered set of behavior. And so we'll train a new model based on that altered set of behavior, and we'll go back and forth over and over again. So this is what's commonly used in practice in the industry. And it actually has three problems. So the first is that it can make extremely bad decisions, especially in the initial steps. So you may be making decisions that are very easy to game and that lead to bad outcomes. And the second is that it may not actually land on an equilibrium in the end. And we'll show some examples of that. And the third, even if it does land on an equilibrium, it is unlikely to be the optimal one. And so the point of this paper is to suggest, well, instead of doing this process of back and forth optimization in the real world, where your decisions carry risks and it's costly, let's do that back and forth in a model. And we're going to solve for the decision rule Y star that's optimal, anticipating that people will manipulate it. And so this is just going to, what this means is we're going to have a model, but then once we do that, we'll be able to kind of short circuit this whole process. I'll pause there in case there are any questions.
Actually, I have one. So these X's are the manipulations and Y's are the outcome of the machine learning algorithm?
Yeah, so you could think of the X's, and this will become more clear in a slide. The X's are the features, but they can be manipulated.
Mm-hmm. Okay.
Great. So to think about what we're doing, we might observe some training data where the behavior is not incentivized. So those X's are going to be a function of a beta equal to 0. And we know the outcomes in that training data. But then what we want to do is we want to maximize performance not in our training data, but in a different distribution where the X's have shifted, where behavior has been incentivized by this new decision rule. Because then we're going to implement this Y as a function of X. And in fact, this testing distribution is what we're going to observe. So to make that more concrete, we're going to introduce a simple model. And this model is going to be coming from like a poverty targeting idea. So there's a policymaker that wants to give each individual I some reward yi based on their underlying type x under bar I. And so there's some equation. This is what they would ideally like to do, but they don't see the underlying type. They see a behavior xi, and the behavior could be manipulated. And so the policymaker is going to choose some decision rule y hat as a function of x, which pays that individual some amount beta times their x plus some constant. Now, I likes getting these rewards. And so their utility includes that payment, y hat. And then they incur some cost of manipulation if their behaviors x differ from their type. And we came up with a simple expression for that cost. We're going to assume that it's quadratic. And so it's minimized, the cost itself is minimized at the bliss behavior at the individual's type, but you may want to deviate from that if there are rewards associated with that. And those costs can differ in two ways. So first, they can differ between individuals. So some people may find it easy to manipulate behavior and others may find it more difficult. And second, they can differ between types of behaviors or different features. So in the mobile phone credit scoring example that we'll talk about later, it turns out it's pretty easy to manipulate outgoing calls. You can just call a bunch of people, but harder to manipulate incoming calls. You'd have to get a bunch of people to call you. Then given this model, we can derive the optimal behavior that we'd observe as a function of beta. And that's going to equal the following. Now, if that beta is 0, so if there's no reward based on your behavior, then it's just going to equal your type. People aren't going to manipulate their behavior. But as you start placing incentives, as you start putting weight on beta, people shift their behavior in the direction of beta, but downweighted by the cost of changing the behavior. So now if we think about how to use that in a decision rule, if we use a standard machine learning decision rule, that is going to assume that there's no manipulation. So whatever data we see in our training data set is drawn from the same distribution that we'll see when we actually implement the decision. And so in the case of OLS, this is what the loss function looks like. But the principle is the same even with fancier machine learning estimators. Your X's are going to be fixed. Now, our strategy robust decision rule is instead going to anticipate manipulation. So it's going to recognize that as I start to place weight on beta, in fact, people are going to change their behavior to try to get more rewards. And so these X's are a function of beta. And so this means that for a linear decision rule, we're going to get a nonlinear least squares estimator of beta. And that simple model on the previous slide tells us exactly how this X varies with this incentive. And so together, this gives us a fairly simple expression for a strategy robust decision rule. So if you think about our method, you can think of it as another linear decision rule or another estimator for linear decision rules that you can add to your toolbox. So you're familiar with ordinary least squares, which is a linear estimator that maximizes in-sample fit. But you are also familiar with other types of estimators that are also linear, but that sacrifice in-sample fit in service of other objectives. So for example, you might be familiar with instrumental variables, which is going to give up some in-sample fit to get a causal estimate of beta, or penalized least squares like lasso or ridge, which are going to sacrifice some in-sample fit to do better on out-of-sample fit on samples drawn from the same environment. What we're thinking about in this project is actually something different, which is counterfactual fit. So we're going to also have a linear estimator, but we're going to sacrifice the fit within the sample, the training sample we observe, in order to do better on a counterfactual sample. In the counterfactual, where agents best respond to that decision rule. And that's going to become more clear as we go through the talk. But let me pause there in case there are any questions about the model.
I have a question. I didn't really follow how the CI was formulated.
Sure. So the C function or the CI matrix?
Yeah, the CI matrix.
Sure. So basically there's the diagonal costs, which are if you incentivize behavior I, how much does behavior I change? And then the off diagonals are if I incentivize behavior I, how much does behavior J change? So that gives us a matrix. In practice, for our experiment, we're going to just look at the diagonal. Does that help?
Yeah, absolutely. Thank you.
Great. So let's see some examples to see how this works. So I'm going to show you some Monte Carlo simulations. And I want you to imagine a situation where we have two features to choose from. And let's imagine one is outgoing calls and one is incoming calls. And it just turns out that outgoing calls is most predictive in the baseline data you observe, but we can also guess that it's probably going to be easier to manipulate. So if I use OLS, then it's going to put more weight on outgoing calls than incoming calls. And it doesn't matter how costly it is to manipulate behavior, it's always going to do the same thing. That's going to work great if manipulation is very costly. But as manipulation becomes cheaper, this starts to make extremely poor decisions. And so you might think, well, you know, what we could do is we could use lasso and we could just penalize this. It turns out lasso is going to do exactly the wrong thing here. So lasso is going to look at your training data and think about, well, which variable of these two is most predictive? And it's going to keep them both in, and then it's going to kick out the one that's least predictive in your training data. And it turns out the one that's most predictive in your training data is outgoing calls, and it's not the one that we actually want to keep in the regression. So our procedure is going to balance these two things. When manipulation is very costly, it approaches OLS. But as manipulation becomes cheaper, then it's going to shift weight to the indicators that are harder to manipulate. And this performs much better in these simulations. Another example which is quite similar, again, we have X1 here is most predictive, but also easiest to manipulate, most predictive in the baseline data. And here, if you see this in numbers, if you run OLS, that looks great when there's no manipulation. But as soon as people are allowed to manipulate their behavior, the performance just deteriorates rapidly. And so you might then want to do the industry approach and just retrain this over and over. It turns out in this case, that doesn't actually converge to an equilibrium. It just bounces between two extremes. It finds out people aren't manipulating this feature, let's include it. Oh, people are manipulating this feature, let's kick it out, essentially. And so our approach instead gives up some performance in the case where there's no manipulation, but does much better when there actually is. One kind of small aside is that I've been talking about manipulation as a problem, and in most cases it is, but manipulation can actually improve performance. So if the people who you want to give rewards to find it easier to manipulate, then manipulation itself could be a signal that you could use. And so that logic is the same as in Spence's 1973 paper on education signaling. And you can come up with simulations that find performance improves under manipulation. And in those, our method actually takes advantage of that signaling power and does a bit better than OLS. So next, we're gonna test this method in an experiment. And the goal here was to create an environment where desirable resources, some yi's, were allocated based on behaviors, these xi's. We're going to estimate all the pieces of this model, the types, costs of manipulation, and then estimate our models and then test them out. And we're going to pay people based on both a naive model, which is standard OLS, and a robust model. And then we're going to compute the equilibrium cost of transparency, which will become clear in a little bit. And I should flag here, I should have mentioned this in a few slides before, that we are focusing on linear models here, which are not the most sophisticated machine learning models you can think of, because we want to isolate down to kind of the core of this manipulation problem. But the same intuition for how to deal with this in the linear case could extend to these fancier methods. And if that's something you're interested in, I'm happy to chat more. So the context that we're going to do our experiment in is digital credit in Kenya. And so as a way of background, there are about 1.7 billion people who lack access to formal financial services. But the majority of the adults in that group actually now have mobile phones. And so it's now possible to reach them without physical bank branches. About 10 years ago, I suggested a way to, but one of the problems is that these people tend to not have credit scores. So they don't have formal financial histories. And so about 10 years ago, I suggested that, well, maybe just the patterns in how a person uses their mobile phone could be used to predict whether they are likely to repay a loan. And it turns out that that's true. You can come up with alternative credit scores based just on how a person uses their mobile phone. And that is now widely used. So there are now digital credit products around the world that use this alternative credit score. And you can basically request a loan on your phone. If you're approved, then you're sent the money instantly via mobile money, which you can then cash out at a vendor. This has taken off, I think, far more than any of us working in this field would have expected. In Kenya, 27% of adults have taken out a digital credit loan. And worldwide, firms providing these loans have gathered over 450 million in venture capital funding. A few years ago, there were over 68 products, and I assume that there are many more now. And you can see products kind of around the world. So this is a huge new industry that uses this machine learning method. And like many cases where important decisions are made using algorithms, it faces the same two problems that we talked about earlier. So the first is that these vendors have faced cases of manipulation. So some individuals have figured out how to manipulate these algorithms to get loans that they don't intend to repay. And that's caused instability and made it so that these firms may not be able to serve the riskiest borrowers. You can also see people sharing tips on online forums. A second thing that this threat of manipulation has done is that many of the firms initially were more transparent about how they made these decisions and how people were denied or approved for credit, but have since become more opaque. They give less details. So our experiment is going to step in here, and we decided to build a new smartphone app. This is together with the Busara Center for Behavioral Economics in Nairobi. And that app has 3 features. So the first is that it collects the same behavioral data as a digital credit app. And so here's a screenshot of the Android permissions, for example. And so this is aggregate statistics about the times you place calls, the number of text messages sent and received, apps used, etc. And so while this data is anonymous and the researchers don't know the individuals' names or the contents of any communication, it also is sensitive. And so we worked very hard with the Busara Center to make sure that people knew what data they were revealing to the research team. And overall, people were excited about it and they trusted the Busara Center for the study. The reason they were excited about the study was mostly because of the second point, which is that this is an app that provides rewards based on your behavior. So for example, this is a person who received a reward of 15 Kenyan shillings for each sports type app that they used that week. So each week, each individual would receive a different challenge like this. Some were simple, like you'll get a reward for each sports type app, and others were more complex. So this is an example where the app is going to try to infer the type of person this is. So originally we wanted to infer whether someone would be a good credit risk by giving them a loan. It turns out that was logistically very difficult to do. So we're going to try to infer other attributes of them. So for example, their income level, whether their education level, and so on. And this is an example of a challenge. So you will receive a reward of up to 1,000 shillings if this app guesses that you're a high income earner based on your calls, texts, and app use. This challenge is opaque. It doesn't tell you how the algorithm works. We also randomly varied the transparency of the algorithm. So some people also saw the full details of the algorithm, exactly the coefficients of the model, and we gave them a tool they could use to predict their earnings. I'll pause there in case there are any questions so far.
So I have a general question about this approach. I guess my question is like about the privacy of the users. I mean, I understand that like these apps are, I mean, they use it with their own consent, but and I understand it that like if it's like in a developing country like Kenya, it's very helpful for the people who don't have like a credit history to have like other tools to use for like apply for a credit card or I don't know, get a loan, something like that. But if these algorithms get used in I don't know, dictatorships, like there are things that you read that, you know, people are not allowed to get loans because of their behaviors that have been such and such. Like, how would you address those issues?
Those are huge concerns. And actually, as part of this study in the initial focus groups we did, we wanted to get a sense of, so people were very familiar with these apps and knew that they could get a digital credit loan if they wanted one. And we were trying to get a sense of, did they know what data was being collected and how it was used and how these decisions were made. And we found that most of the people that we talked to in this population really did not understand. So I think regulators are very concerned about that and are working on that. Partly this also comes down to transparency. So if you're being transparent about how this decision is made, then it's very clear to people what information is being gathered. So I mean, I think it's a combination of, I think, better information in people's hands, regulators that offer rules that help people understand the decisions that they're making, and then hopefully, I'm very hopeful that we'll eventually be able to be more transparent in how these decisions are actually being made. But I think you're absolutely right. I think there's a lot of work to be done on those questions. I don't think there's a easy answer for those things.
Yeah, I also think like transparency is like, I can see that transparency can be a solution to this problem, but it can be a solution to this problem in the countries who have a well-functioning democracy. Like if you are living in a country who has like a complete dictatorship, everything can be transparent and they can be like still against you. So that's yeah, these are, I know there is no answer to this question, but it's a broad question, I guess, but yeah.
Yeah, and yeah, in countries that do not have representative governance or where there's potential for harm, I think those are huge concerns with these technologies in general. And yeah, I do hope that we see more work on that.
Yeah, thank you.
Great. So essentially the experiment has a couple parts. So in the first, we're going to just estimate the different parameters of the model. One, by surveying people as they come in, and we'll get a sense of their income, et cetera, these things that we want to predict. And then we're just going to observe their behavior before we incentivize them. And then we're going to pay them with simple challenges where we incentivize one behavior or another. We're going to use all this information to estimate our lasso model and our robust model. And then the final stage, we're going to test this by implementing it. And this is going to be those complex challenges that are either going to be opaque or transparent, where we pay people a reward if the app guesses that you're a certain type of person. So the first outcome is that, you know, how you use your phone is predictive of the type of person you are. This isn't surprising. A lot of other studies have found this. We actually don't find incredibly strong relationships between, for example, how you use your phone and monthly income, marital status, intelligence measured via Ravens, or whether you're popular per your SMS behavior. But there is some correlation. married people seem to make more calls, but fewer calls to non-contacts, and higher income people, and also have more unique contacts. But what we find in our study in the next part is a bit more interesting, which is when you incentivize people to change behavior, they do so. So if the challenge says you will receive X shillings for each missed call that you receive, then those people make more missed calls. And they not only change their number of missed calls, but they also change some other behaviors. They tend to call more people during the weekday and also send more text messages. And you can imagine reasons why you might do that. You might call more people and tell them that this is what you're doing. Or sometimes you might try to leave a missed call and people may answer it, or you may text them. So there is some relationship between these behaviors. And so we did that for many different behaviors, incentivizing them. And there are two things to note. So the first is that incentivizing a behavior typically results in that behavior changing. So these features are all manipulable. Missed calls, number of times you charge your battery, calls to non-contacts, text messages sent. And the second thing is that they're differentially manipulable. So if we pay you to manipulate text messages, turns out that is much more manipulable than missed calls or the number of people called during the workday. And so that differential manipulation is going to, our method is going to exploit that. And then this is like a bit more detail than you probably need, but we essentially will use the combination of these weeks where we've assigned no challenge and these weeks where we've assigned these simple challenges to estimate all the parameters of our model, including the types. Those are going to be inferred from these control weeks, as well as the manipulation costs, which we're going to break down into gaming ability. Some people find it easier to game than others, and this ease of manipulation by feature type. And there's a lot more details here that you don't need to know. So then once we've recovered those parameters, we can then estimate the decision rules. We're going to use lasso. So just like I showed before, we're going to have the start of the OLS loss function, but then with a lasso penalization. We're going to include that same penalization in our robust model, but we're also going to anticipate the manipulation that we're going to observe when we actually implement this. So what we find then when we estimate these costs is fairly intuitive. So text messages, which are cheap in this context, are easier to manipulate than calls. Outgoing communication tends to be easier to manipulate than incoming communication. And we also found that things that were hard to explain were harder to manipulate. And you might think that in practice, eventually people will be able to figure those things out, but that is something that we found. Try as much as we could to describe some of these things. And so essentially we're able to estimate these manipulation costs between features and then also by person. And we find that people who have high tech skills tend to find it easier to manipulate their behavior. But there's also a lot of idiosyncratic reasons. So there's a lot of other variation that's just random between some people finding it easy to manipulate and others finding it more difficult. So let me pause there. Are there any more questions?
So is ease of manipulation a single parameter per feature that can be manipulated?
Yeah, so we're going to only be looking at the diagonal of that cost matrix. So there's going to essentially be two pieces to it. It's going to be the diagonal of that cost matrix, which is exactly what you said. But then there's also going to be this gamma parameter that is different between different people.
So I'm wondering though, like, it seems to me like how easy something is to manipulate and how worth it is to manipulate are different things. So if you play with the amount of money, like, you know, no amount of money is going to make me go out and kill someone. But, you know, if you gave me a lot of money, I might eat a raw onion or something. And that's easy for me to do. I could eat 100 raw onions if you paid me a lot of money for each one.
Perfect. Yes.
But I could only cut off so many of my toes before I run out of toes.
These are dark manipulations. Sure. So this is a fantastic point. And so you're absolutely right. So these C here, these costs are measuring how costly is it for me to manipulate these things. But then you want to weigh those against the benefits. And the benefits, I'm not going to go all the way back, but the benefits are actually, those depend on the beta. Because the higher the beta is, the more benefit I have for manipulating that behavior. And so that is the wrinkle, that the costs are some fixed thing that we can measure, but the benefits are an equilibrium object, because they're going to depend on how predictive the underlying data is for those features, as well as the costs, because I don't want to put too much weight on things that are cheap to manipulate, because then those will no longer be predictive. So those are like, some of these behaviors are going to be slippery, they're going to shift around a lot, and others are not going to shift around as much. And so this model is going to use these estimated costs and then find the equilibrium that matches those with the benefits, which it computes based on the surface of the data. But that's a great point. So next, we actually started implementing these decision rules, and we told people, for example, well, so if we just measure a naive beta, so this is a lasso decision rule with 3 coefficients, and we want to predict income. We want to pay people based on income. It turns out that people with higher income place more outgoing calls, receive more texts, but send fewer texts. And if we just tell people that they're going to be rewarded based on whether you're classified as a high income earner, and we don't tell them how that classification algorithm works, what we see is mostly noise and mostly in the wrong direction. So people are not gaming this algorithm in a way that indicates they know how it works. If we tell them exactly how this algorithm works with this transparent treatment, it's still quite noisy, but it's mostly in the right direction, or more in the right direction. So, so this is some suggestion that people are gaming these algorithms once they know how they work. So we then tested not only this naive estimate of our beta, but also the more robust one. And the robust one is going to do 2 things. So first, it's going to select different features. So incoming texts is pretty easy to manipulate, and it swapped that out for evening texts. The second thing that it does is it also tends to shrink behaviors, especially those that are easy to manipulate. And so then we implemented this in practice. We paid people based on this, and then saw based on their behavior when they knew how this decision rule worked, what the prediction error was. And these are root mean squared errors, which are measured in dollar terms. And what we find is that in the training data, when there's no manipulation, the naive model does a little bit better. So that makes sense. The naive model is trying to maximize fit in the training data. And you give up a little bit of performance with ours. But when you actually implement this and people are told how it works, then the robust model does better. And also, the gap between these is also smaller. So it's less impacted by the strategic behavior. So it's a bit more stable. So this is quite good news because it indicates that we can make things that are more robust to manipulation. And to think a little bit about what is going on underneath this, if you think of standard machine learning estimators, these all consider features by how predictive they are in training data. Now, there's a lot of different ways to measure predictiveness. One is the max R squared, just as a one variable. But you could also consider predictiveness conditioning on other variables and so on. And so there's a lot of different ways you could measure this. But essentially, you can come up with some measure and then rank variables and decide which ones to include. It looks like this variable does quite well, and so we might want to include that. Our method says, well, actually, these variables that look like they were all on a line, that all had different predictive performance in your training data, if you actually were to use them, people's behavior would change, and they would change by different amounts. And it turns out that this variable that looked like it was so useful because it looked so predictive in our training data is actually one of the cheapest variables to manipulate. And in general, we see this big spread where variables that look equally predictive in training data actually are differentially costly by several orders of magnitude to manipulate. And so the key question here is, how do we estimate this new object, which we're calling C, but really it's the function X as a function of beta? How much do your behaviors change as a function of the incentives? Those will both measure this counterfactual shift. And so our paper argues that if you want to make good decisions in a context where people have incentives to change their behavior, that you need to take into account this differential shift. So what we've done, and feel free to interrupt. Actually, I'll pause here if you have more questions, but feel free to interrupt in general if you have questions. Okay, so what we've done in this experiment is we've estimated this object by experimenting and giving people rewards with the randomized controlled trial. That's something that we could do in this context. I shouldn't say easily because it was a lot of work, but it's something that works well in this context. But in general, we might want other ways to measure this. So one approach that we also tried was to ask experts to see if you just ask people to gauge how easy it is to manipulate different behaviors, can they do a good job? And so we sent a survey to 177 different academics, implementers, and MTurkers, including some people at Brown. And it turns out if you were a part of this sample, you did quite well. We do find a decently large correlation between what experts predict will be manipulable and what actually is in our experiment. So this would be one way. There's also many other ways that we have imagined that you could estimate this object by like decomposing the cost into its components, or matrix completion, or less obtrusive experiments. So I think there's a lot of interesting work to be done here in follow-ups. And if you are interested, I'm happy to chat more. And so that this is kind of one point, that if you have this object, you can make better decisions that are more robust and less risky. And then the next question to talk about is transparency. And so I think we can all agree that there are a lot of virtues of transparency. But one thing that hasn't come up too much, but does come up if you talk with implementers, is that there's concern that the more you reveal about how your decisions are made, that they may cease to make as good decisions. And that is what we find in our experiment. So if you look at our opaque treatment, where we didn't tell people how the decision rule worked, and then compare that to the transparent rule where we did, with the naive lasso model, going to transparency reduced performance by 25%, which is substantial. And so you may need to weigh the cost, this cost of transparency against the benefits. But the good news is that if you used our robust model, that cost of transparency is actually much lower because it performs quite a bit better when people are told exactly how this decision rule works. And we find that this cost of transparency is below 8%. Now, and so I think this is an important thing to keep in mind in policy discussions about transparency, and hopefully we can get this cost of transparency lower, and so it'll be more attractive to make transparent decisions. One thing to flag is that the way that we computed this table involved actually telling some people how the decision rule works. In practice, if you wanted to try this with Google, for example, and you said we were going to take 100 people or 1,000 people and we're going to tell them exactly how the Google algorithm works, they probably would tell other people, and pretty soon everyone would know. So most firms or implementers would not want to reveal, if they're concerned about transparency, they wouldn't want to be transparent even in an experiment. And so one of the neat things about our model is that it actually allows us to bound this cost of transparency even without revealing the model. And we can do that because we can predict the performance of the model when there's no when it's too costly to manipulate, when the costs are infinite, and subtract the difference between how we would expect people to manipulate even before actually implementing it. So this is a little nuanced, but I think this is quite promising for these discussions. So I'll wrap up the talk about manipulation-proof machine learning and then pause for some questions. And then if we still have time, I also have some stuff on welfare that we can talk about for a few minutes after that. But to wrap up this project, you can think of this as a framework for prediction in the face of manipulation, which has both a theory part and an empirical part. And in the empirical part, we find that even new users of smartphones manipulate digital behavior when there are incentives to do so, that our strategy robust estimators can improve performance. And we're hopeful that this suggests a path forward for digital decisions that are more transparent. Now, there's obviously, what we've done today is fairly simple. There's obviously a lot of complexities that you can add, like nonlinear decision rules or randomized decision rules, or cases where people have beliefs about these decisions, that they know something, but not everything. And we hope that this kind of serves as a framework. One other thing to mention is here we've been focused on predictive performance, but manipulation incurs cost to the people who manipulate them. So if you're a social planner, you may want to take that into account. And so you may make a different decision about the model to use than a firm would. And overall, this suggests an approach where when you're using machine learning estimators that interact with people or that are used to take actions, that you can include models of those people and include models of the social systems within your estimators. And what we've shown today presents a machine learning interpretation of the Lucas critique, which if you study some macroeconomics, you may have heard of. So I'll pause there in case there are more questions.
So I have a question from the previous slide. So can you give us an intuition why the equilibrium cost of transparency becomes less? Because you would think that, maybe I'm understanding this definition wrong, but you would think that if things are transparent, people would be able to manipulate things like more effectively. So why does it go down when you allow them to do that?
Great question. So it's a little bit nuanced. So basically, if we knew that people weren't going to manipulate, then we might want to use OLS or lasso in this case. And it turns out when we do that, we get a performance of about $4 RMSE. Now, if we if we then use that same model and kept the model fixed and then revealed it to people, that performance would deteriorate by about 25%. But now if we were revealing the model to people, then that first model, the naive model, is not the best one to use. Because we would want to take into account the fact that these behaviors would shift once people take that into account. And so you can think of, so this comparison is based on what is the model that we would expect to be optimal when it's opaque versus the one that we expect to be optimal when it's actually transparent, which is this robust model. And so you can think of this as trying to estimate, if we not only make our models transparent, but also adjust our models to the best model under transparency, what does that cost? And that is the cost that we find is 8%.
Thank you.
Sure. Great. Any other questions? All right. I think did we have a few more minutes?
It depends how many minutes do you need.
Oh, I can stop now, or I have like a few more if we want to.
If you think you need like 2 or 3 more minutes, we can do that, but maybe not more than that.
No, let's stop it here then. That's perfect.
Okay, thank you very much.
Thank you all so much.
So if there are not many questions, okay, thanks. Okay, so I guess we move to Jessica now. Can you share your slides, or do I have to make you a co-host?
Oh, sorry. I thought you were gonna do the intro first. That's fine.
Oh, okay, yeah, I can do that, but yeah. I was still hearing, I'm not sure if it's only me or other people are hearing that. Like, can you try can you turn on your microphone?
Is this any better?
I hear some parts, but I don't know if other people are hearing.
I just switched to a different mic. Is that look any better? Let me try and switch to a different laptop. Sorry about this. Okay, is this audio any better?
Yeah, it's much better now. Okay, so while you are sharing your slides, I will introduce you. Okay, our next speaker is Jessica Dye, who is a senior at Brown University studying computer science. Jessica is broadly interested in fair machine learning and its limitations, especially when applied to the real world. In addition to research, Jessica has been involved in developing the first iteration of Brown Computer Science's socially responsible computing undergraduate program. Okay, so, and today she's going to tell us about fair machine learning under partial compliance.
Cool. So, hi, I'm Jessica. This is my project on fair machine learning under partial compliance. This is work I did as a visiting student at Carnegie Mellon in this past summer, remotely, obviously. So, oh man, my keyboard is, sorry, I switched laptops just now, so all my Bluetooth is like messed up now. Okay, cool. So to start off, I wanted to sort of discuss how most work in FairML works now. We focus mostly on a single decision maker. So we arrive at a predictive model by training some machine learning algorithm on a historical training data set. And we usually assume that the model is used as follows. So it takes in data about individuals and spits out predictions about them that are maybe then used for decisions down the line. So some of that might be defining what it means for the specific outputs to be fair, what does a fair distribution look like, or figuring out ways to make this model behave such that its output satisfies one of those definitions of fairness. So how can we post-process the outputs of a classifier so that its predictions are fair? Can we add a constraint to the optimization so that it produces a fair classifier? But in this work, we're concerned with sort of a setting where we have multiple decision makers. So in the real world, we might have multiple decision makers. They might be competing with one another. So for example, one common setting in FairML is the provision of loans, but there's obviously not one bank for the whole world that like every single person has to apply to. There are actually several different banks that can be providing loans. And more crucially, only some of them might care about fairness. So each of these banks might have a different policy for how they allocate loans. And the last thing here is that individuals can choose where to apply. They're not constrained to only applying to a specific institution. And so I wanted to highlight the second point here about only some institutions caring about fairness. So this is something that political philosophers describe as partial compliance. So one might argue that all decision makers have a responsibility to act fairly, but in reality, only some are going to do so voluntarily. And this is sort of a very intuitive, natural occurrence when we see tech companies prioritizing profit over XYZ, like social responsibility. In this case specifically, when we have multiple decision makers acting differently with different policies, this means we can't consider their decisions in a vacuum. And so that's for two reasons. First is interactive effects between the decisions of different institutions. So for example, if I apply to institution X and get a favorable outcome, like I'm hired or I get a loan, then I'm not then also going to apply to institution Y. And so the decisions made by each of the institutions are going to influence what decisions are available to other institutions. And then the second reason is strategic decision making. So for example, if it's known that institution X has particular policies that might be more favorable to someone, then they will be more likely to apply to institution X over another institution. So in this work, what we're asking is not how do we make an algorithm fair, but rather what are the consequences of a fairness intervention? And more specifically, what's the impact of partial compliance in light of the dynamic interactions that might emerge between individuals and institutions? How should that shape the way we think about what we define as fairness and how we want to approach regulating it? So our approach for answering this question is setting up a really simple simulation of a job market. So at every time step, we have some pool of applicants, a group of employers, and at every time step, individuals are going to apply to those employers. The employers make some hiring decisions, and we end up with a set of outcomes. And so this happens at every time step we run. This is a simulation we're running over a long period of time. And so one thing I wanted to note about simulations is that we aren't claiming that this is how things work in the real world at all, but we think that having a really simple setup allows us to isolate specifically the consequences of partial compliance as a phenomenon, even when we make sort of the mildest, most basic assumptions about how everything interacts with each other. And one thing to note here also is like simulations, also a very common methodology in philosophy, specifically in considering long-term impacts of particular policies. So to sort of dig in on this a little bit more, I wanted to give some more context on the population. So all individuals in our simulation are characterized by their group membership and their score. So exactly two things. And so we have two groups, an advantage group, which we'll call group A, and a disadvantage group, which we'll call group B. And the score represents some notion of how good they might be at the job. Those are normally distributed for both groups, but group B has a slightly lower mean score. And something I wanted to note here about the score is that we don't necessarily take a position on like the extent to which the observed score correlates to some true underlying notion of skill or aptitude. Our results are relevant regardless of sort of the mapping between observed and true score. And the next key part of our experiment is the hiring policy. So how do employers decide who to hire? So the first sort of generic, or what we're going to call a non-compliant policy, is a hiring policy that's completely group agnostic, and this employer will just sort all of their applicants by score and hire the highest scoring applicants, regardless of group membership. And now we have for the compliant policy, we have two flavors, which these employers care about fairness and satisfy some version of demographic parity in their hiring, but they are satisfying demographic parity with regards to sort of a different number. So for a global parity compliant employer, they're going to be satisfying demographic parity with respect to the global population demographics. So since group B is 25% of the entire population, no matter what the applicant pool looks like for a global parity employer, they're always going to make sure 25% of their hires are from group B. A local parity policy, on the other hand, is going to satisfy demographic parity with respect to the applicants it's received at the current time step. So even if group B is 25% of the entire population, if the local parity employer receives applications that are 40% Group B, then 40% of their hires will also be from Group B. And I also wanted to make a quick note on demographic parity here. So we're not claiming that this is exactly what fairness is or how it ought to be measured, but this is actually a super common and widely used metric in current practice, especially in the context of employment law. And so we use this operationalization as a starting point. And also, if you think about, there's like some definitions of fairness that are concerned with calibration towards ground truth and accuracy and all of that. And so you can almost view the generic non-compliant policy as satisfying a different definition of fairness that cares more about accuracy than sort of this demographic parity outcome distribution. So one other way to view this is a comparison of when employers have heterogeneous interpretations of what it means to be fair. And so the last part of the experimental setup is application strategy. So how do candidates decide where to apply? So the first strategy is static preference. So applicants from both groups have some knowledge that they're likely to do better at one employer type than another. For example, Group B knows they're slightly more likely to be hired at a compliant employer than a non-compliant employer, and vice versa. And so they're always slightly more likely to apply there. And so this represents people in the simulation have some limited knowledge about the environment. And then the second strategy is what we're calling dynamic preference. So applicants from each group are able to update their preferences for employers based on which employer type was more favorable to them in previous rounds. So this sort of represents a situation where at each time step, the applicants are able to access new information about the system. And so finally, before we get into our results, I just wanted to sort of give a quick summary of how our experiment was set up. So basically, we vary the number of compliant institutions from 0% compliance to 100% compliance. And then for each number compliant, we run 10 trials of the simulation. In each trial, we run the simulation until it reaches equilibrium, and then we run for some additional number of time steps. And so we calculate statistics for each trial based on the post-equilibrium time steps. So in all of the graphs that you're about to see, one dot reflects statistics calculated from a single trial. So we have a bunch more results and discussion in our full paper, but today I wanted to talk about these three, which I think are the most interesting. So the first one is something we're called sublinear gain. So on this graph, the x-axis is the percent of institutions which are compliant, and on the y-axis is something we're calling percent benefit. And what that really is the measure of demographic parity scaled by the baseline demographic parity at 0% compliance. So in our simulation specifically, the raw demographic parity ranged from 0.75 to 1, and then so we rescaled that so that a demographic parity score of 0.75 reflects 0% benefit, because that's the overall demographic parity when no institutions are compliant. And so this light orange diagonal line represents linear gain, where each additional compliant institution brings in the same amount of benefit. And so obviously that is not the case here. The true curve that's represented by the blue dots is always below the diagonal line, which means that for any K% compliance, there will always be strictly less than K% benefit received in aggregate. And what that means sort of intuitively is that even though like 50% of institutions are employing the FAIR policy and hiring 25% of the applicants from Group B, overall, we're not seeing 50% of the way towards like perfect parity at 50% compliance. And for some intuition for why that's the case, that sort of lies in the applicant strategy. So when applicants are more likely to apply to one institution type over another, that means that the non-compliant employers are actually seeing fewer applicants from Group B, which means that they then hire even fewer applicants from Group B. So even though the compliant employers are sort of doing their fair share of hiring from Group B, applicant preference means that the distribution of applicants at the non-compliant employers has changed. And so this is with the simplest strategy of static preference, but when candidates are able to adapt to new information, and so this is the adaptive strategy, sublinear gain gets even worse. So now at even more than 80% compliance, we're still barely getting less than 50% of the benefit. And so in this case, why this happens is when individuals are able to update their preferences for where to apply over the time scale of the simulation. Over time, applicants from Group B learn that it's just beneficial for them to always be applying to the compliant employers, which means that the non-compliant employers are seeing even less. So it's a similar effect as this previous case, but because they're able to update their strategy over time, this sublinear gain effect is more dramatic. And so the next result is sort of the emergence of segregation, specifically when applicant strategy is adaptive and compliant employers are using local policy. So as a reminder, that means that compliant employers are hiring exactly the percentage from Group B as they're getting in their applicant pool, regardless of the overall global demographics. So this is plotting the same information as before. It's strange, kind of strange behavior, but it honestly looks pretty good, right? So we're reaching basically full benefits, 100% of the benefit, which means like demographic parity equals 1 at around like 25 or 30% compliance. But if we look at a graph of the demographic composition of who actually gets hired, that tells a different story. So this graph on the right shows what percentage of hires were from Group B in each institution type. And so you can see the pink line, the non-compliant employers, goes down to 0 at 20% compliant, which means that if more than 20% of employers are using some sort of fairness policy, then the non-compliant employers actually hire nobody from Group B. And so as before, the reason this happens is because the applicants are learning that basically it's always more favorable to apply to a compliant institution over a non-compliant institution. And in this case, because employers are satisfying local parity, that means that, you know, if they're getting more applicants from Group B, they're hiring even more from Group B. And then at the next time step, even more applicants from Group B decide to hire, to apply to the compliant institution. So it's sort of like at a certain point around like 20, 30% compliant, Group B is only applying to the compliant institutions and not applying at all to the non-compliant institutions. So in this case, what appears to be an improvement in overall demographic parity actually is coming at the cost of extreme segregation. And this, of course, also raises really interesting questions about the extent to which a global measurement of fairness via demographic parity is sufficient to capture what's actually desired from a given fairness intervention. And so the last result I wanted to talk about is auditing, and specifically what we might be able to get out of auditing individual employers. So, you know, we've seen from results 1 and 2 that partial compliance can have a substantial impact on what the world looks like. And so maybe we want to determine, you know, which employers are using a compliant policy and which ones are not. But what we're actually finding is that this may be harder than it seems. So let's say we ask, what percentage of applicants from each group do you hire to each employer type? And in this case, compliant and non-compliant employers are actually indistinguishable. So the top line, which is hires from Group A for both institution types, for non-compliant and compliant, those are basically on top of each other. And same thing with Group B. That is, compliant institutions hire the same percentage of applicants from Group A as non-compliant employers, and same thing with Group B. So if an auditor was asking this question, then the two types of institutions are actually indistinguishable, even though they have really different hiring policies. And so this result is not to say, you know, that auditing is hopeless or we just shouldn't do it, but rather that current auditing practices because they focus on a single decision maker at a time, might be ineffective. And therefore, we sort of need a radical rethinking of how to do this, because the results that you might get from auditing a specific decision maker have to be put in conversation with what sort of the rest of the world or the market is doing. And actually, there is a good amount of auditing literature out there, especially in the past few years, and a couple of real world case studies of how do we audit for fairness. And all of those are sort of focused on a single decision maker, a single company, a single algorithm at a time. And that's for good reason. But what these results are suggesting is that they don't necessarily present the full picture. And so a couple of key takeaways here are that, one, partial compliance and dynamic behavior that arises from partial compliance can drastically impact the downstream effects of intended fair policies, and more specifically, the evaluation of fair algorithms, whether it's in the context of regulation or just in terms of, characterizing their behavior and determining whether or not they're being quote unquote fair, has to consider the wider environment of deployment. And so at this point, we don't have prescriptive solutions for how to do this, but we think this work illustrates the complexity that arises when we consider partial compliance, and raises some questions for future work in terms of understanding how an individual algorithm might relate to the rest of the world. And that's it. Thanks.
Thanks. Are there any questions for Jessica? Okay, I have, yeah. Yangming?
Yeah. So I'm not sure if I got the whole model, but I'm wondering if the following will be an implication of the model, or like, do you think so? Suppose we see that some company or some organization, right? They haven't been able to hire very many folks from underrepresented groups, and then then they might say things like, oh, it's a pipeline problem, right? We haven't got enough applicants from those groups. Do you think your results give us some additional reason to think, no, actually, that's not a good excuse, right? Yeah.
Yeah, that's a really interesting question, because actually the original motivation for partial compliance questions in philosophy is to ask what like an individual decision maker is obligated to do. And I think what our results are sort of saying is that it's insufficient to consider only the distribution of applications that you are currently getting in your pipeline, because even if the segregation results were for the local version of parity, which is when you're hiring based on your pipeline, basically. And so what we find is if everyone just continues to do that, then we end up in a situation where there might be some really severe sort of segregation, and that is an excuse for companies to, continue hiring fewer and fewer people, if it's the case that individual applicants have some sense of, is this a good company for people of color? Is this a good company to be at for women? And if individuals are making decisions like that, it's harder and harder for those companies to then get a group that is representative of the world. So yeah, this is sort of really interesting context to the hiring conversation, and when people talk about the pipeline for diversity hiring.
Great. Where can we find your paper, just out of curiosity?
It is on arXiv. If you, there's a couple of workshop versions from NeurIPS, but the full paper right now is on arXiv. If you search fair machine learning under partial compliance, let me.
Thank you.
Yeah.
Cyrus.
So it looked like you observed some phase shifts and things happening at different percentages of compliers. Do you have any theory that would indicate why things happened at specific percentages? And are there any parameters in your model that would influence where those cutoffs are?
Yeah, so there's a couple of things that sort of influence how, like, what exact percentages, what exact percentages things are happening at. So like the mean shift for how big a difference is the average group B score, what percentage of the overall population group B is, and then also like the overall like acceptance rate, how many applicants each company is able to hire at a time step. So those sort of all influence the specific, like calculating where specifically like a transition point happens. But yeah, we haven't really worked out the math specifically, especially for like the local parity and the adaptive strategy cases, just because like we got to a point where there were like too many moving parts. But at least in like the global case with static strategy, it is possible to sort of work out like it is at this percent compliance that we start seeing Y percent of benefit.
Thank you.
Any other questions? Actually, I don't, it's not like a question, it's more like a comment. So I think this setup that you have is maybe similar to like how people choose the major they want to study, like especially the dynamic method you talked about. It's not about like hiring and complying companies and not complying companies. It's more about this dynamic setup that you talked about. It's kind of like if you belong to a racial or gender group, does pursuing this major would be rewardful for you, or the other major would be. So it kind of fits to a similar setup as you are discussing. So just it's just a comment that it like your whole setup reminded me of this problem.
Yeah, and sort of like, there's no real like machine learning happening in this project. It's really about like allocation policy and fair policies in general. So yeah.
Because a lot of people who like complain about like not having so many representatives from a certain minority group in certain disciplines, they say there are not so many applicants or like experts in that field that will be hired later for jobs. But I guess the question is, they do pursue those things because it's more rewarding for them later on. Like it's kind of like a dynamic, as you were describing, that plays into this picture. So yeah, thank you for the very interesting talk. And thanks again, Jessica and Daniel, for interesting talks today. And please join us on Friday at 11:30 for the rest of the talks. Thanks, everybody.